Greetings, dear student. In this particular section, we'll be analyzing a numerical based on Calipron's theorem, which is also known as a three-moment theorem. The statement of numerical is analyze the beam shown in below figure using TMT, three-moment theorem. Also, draw the shear force diagram and bending moment diagram. The given beam is a two-span continuous beam where A and C ends are fixed. B is a mid support. Span AB is of 4 meter having moment of inertia I, and span BC is of 3 meter having moment of inertia I. In span AB, a 50 kN load acts at mid-span, whereas on span BC, a uniformly distributed load of magnitude 10 kN per meter acts. Now, for solution of this, there is a preliminary assumption that Calipron's theorem, or theorem of three moments, is applicable for a continuous beam with simply suppose. Since the end A and C are being fixed, it is very difficult for us to apply directly the Clapeyron's theorem to it. For making it admissible, we have to consider an additional span known as a zero span, where we are going to nullify the effects of rigidity at the point A, partial rigidity at the point A, by assuming an additional span, zero span, and its location as a A dash beyond the fixed end A. Similar way, we are going to assume a zero span for the joint C so as to have the release of a fixity here, and thereby we will consider the joint C as a partially rigid with reference to addition of this span C to C dash, which is known as a zero span. So beyond both the fixed end, we are going to extend the span, and that spans we are going to say it as a zero span, which added to the structure will not make any change or alter the effects of the loading and the end restraints. Now let us begin with the part of analysis. In that case, we have to find out the free bending moment diagram for the given load case along the respective span. So here span A to A dash, the zero span, there is no loading. We can say it is a zero loading here. Whereas for the span A to B, we are having a point load which is acting at a mid span. That's why free bending moment at this particular span will be WL by 4. If I substitute the values here, it will be 50 into 4 by 4, which results into a maximum magnitude of 50 kilonewton meter square. So the point here, the highest point within this figure will be 50 kilonewton meter. Whereas the bending moment profile for the second span B to C, which is subjected to UDL, is given by the relation WL square by 8. If I substitute the value 10 into 3 square by 8, I am going to get it as a 22.5 kilonewton meter. Now, if I talk about the span C to C dash, so the span C to C dash, there is no loading. We will call it as a no load span with zero span. Okay. Now, while analyzing the Calipron's theorem, we need to find out area and under the bending moment profile, free bending moment profile of the beam considered for the analysis. For that, let's try to find out the respective areas for different span of the given beam. The very first column is section, then to that centroid, which is measured from left hand side and right hand side, and the fourth column is related to area, which is measured in mm square. Now A to A dash, we have considered this as a zero span. That's why the left coordinate will be 0, right coordinate will be 0, and there is, since there is no loading, there will be no area of bending moment diagram here. That's why 0. A to B, it is a 4-meter span. If I consider the centroid of this, it is symmetrically placed from both the ends. That's why I can say XL is equals to XR, which is equals to half the span. That's why we can get here X real means the centroid located from left hand side is 2 meter, centroid located from right hand side is 2 meter. If I want to find out area under this curve, the area under this curve is given by the relation 1/2 of the base into height. 1/2 into the base basis of 4 meter into the height 50. So here we will get a resultant as a 100 meter square. Similar the case, we have parabolic distribution of bending moment here in the span B to C. and it is symmetrically placed over the horizontal axis. That's why xr will be equals to xl, where we call it as centroid with reference to left hand side and right hand side will be equal, which will be half of the span. It comes to 1.5 meter, 1.5 meter. If I want to find out area under this curve, it will be 2/3 of the base into height, means 2/3 of the base is 3 into the height 22.5. That result into a value of 45. Now, if we talk about the C to C dash, C to C dash, there is no bending moment. That's why the area will not be there and there will be no centroid concept here. That's why it comes to be 0, 0. I will move towards the execution of or application of your three moment theorem. For this, firstly, I will consider a geometry which will be for applicable for first three supports. So we will consider the profile like A dash A B, means A dash A B means first two spans I am going to consider, and I will call it as 0 and 1, means 0 span and 1 span. 0 span means we have considered here imaginary span, that's all. Okay, next to that we will replace this with the next geometry where we can say A B C and 1 to 2, means I am going to consider the joint A B C and span 1 and 2 for the writing second equation related to Calipron's theorem. Next to that, we will consider the joint B, C, C dash. So, which span will consider here 2 and the 0th span for the right hand side. Likewise, we have three combination, and from this three combination, we are going to get three different relationships. Let's move further. Let's apply the theorem of three moment theorem for span A dash A B. So the theorem says that moment A dash into length of the span A dash plus twice the moment at the midpoint, that is MA, in bracket the span for the first span plus the second span. We can say length A dash plus length AAB plus the moment at the far end, that is B, into LAB, the span LAB, which equals to minus 6 times of AX divided by L, A area under the span A dash into X centroid for A dash divided by length of A dash minus of 6 times of AAB area under of bending under the span A to B, X bar centered under of the bending for the span A to B, and length of the span AB. If I substitute the values here, firstly we have 0 because here we are not considering any moment, that's why 0. This is partially rigid, that's why we get here 2MA 0 plus 4, 0 for the first span, plus MB into 4, that's a 4 meter for the length A to B, minus, since area of this particular diagram is 0, the total entity will be 0, but the second part of this right hand component will be 6 into 100, means the area under the bending profile for the span AB, multiply by the centroid of it 2 meter divided by 4, that is total span. From this we get a relation 8MA plus 4MB is equals to minus 300. Let this be equation number 1. Now we'll move to the second part, the second consideration A, B and C, and we'll apply the three moment theorem for this particular case. So here we'll get a MA into LAB plus 2MB into LAB plus LBC plus MC into LBC minus 6 times of area AB into XAB divided by LAB minus 6 times of ABC into XBC divided by LBC. If I substitute the value here, it is a 4 times of MA plus 2M plus 4 plus 3. 4 is nothing but span A to B and 3 is nothing but the span B to C here. Plus 3 times of MC is equals to minus 6 into 100 into 2 divided by 2, means area under the curve multiplied by the centroid multiplied by 6 divided by 4, minus 6 into area under the second curve multiplied by its centroid 1.5 divided by 3, the centroid with reference to C here. So we get a relation here 4MA plus 14MB plus 3MC is equals to minus 367.5. This is our equation number 2. Now we'll apply the TMT for the third consideration, that is a B, C, C dash. If I apply the TMT equation, I get a relation here MB into LBC plus 2 MC into LBC plus LC C dash plus MC dash LC dash minus 6 ABC area under BC into XBC divided by LBC minus 6 times of area under C to C dash X to C dash divided by LC dash. Since it's a 0 span, the moment will become here, and the area will become here 0, and length will become here 0. So we will get a relation 3 times of mb plus 2 mc in bracket 3 plus 0 plus mc into 0 because length span is 0 minus 6 into 22.5 into 1.5 divided by 3 for the span BC minus 6 into 0 because 0th span was considered. That's why we get a relation 3mb plus 6mc minus 67.5. This is our third equation. So we have here three unknowns and three equations. If you try to solve the equation for the first case, the equation for the second case, the equation for the third case, this simultaneous equation, if you solve, we get a value of moment at the end A as a minus 28.75 kilonewton meter, moment at B equals to minus 17.50 kilonewton meter, and moment at the end C is minus 2.5 kilonewton meter. Now, we'll move towards the preparation of shear force and bending moment diagram. So for this, we'll consider the individual spans here, A and B. And for this, we'll consider the fixity as generated, reactive forces at the end A and B. At end B, I'm going to say it as a RB1 because it's a common joint between the two spans. Half the contribution for will be with reference to AB span and half will be the consideration with reference to BC span. Now, if I apply summation of forces with reference to vertical axis, we get a relation RA plus RB1 equals to 50. Summation of moment about the end A, it will be moment caused by all the loadings over the span towards the point A. So RB into 4, that will have anti-clockwise rotation. That's why minus 4 RB 1 minus of 28.75, that anti-clockwise moment at the end A, plus 50 into 2, the clockwise twist caused by this applied force, plus 17.5, that is the moment which we have received at the end B. After doing this, we get RB1 value, which is equals to 22.18. If I back substitute this in the previous equation, that is a vertical axis summation of vertical forces equation, then we'll get RA equals to 50 minus RB. If we substitute the value respective, we get a value of RA as 27.82. Now we'll consider the second span here, B to C. Since B is a common joint, half contribution I will take from this particular span. That's why RB2 has been represented here. RC is the reactive force at the end C. If I take summation of vertical forces, I will get a relation RB2 plus RC equals to 10 into 3 is 30. If I take moment about B, then I will get a value as if minus 3 times of RC minus 17.50, the anti-clockwise moment at the end B, plus 10 into 3 into 3 by 2, that's the effect due to the rotation effect of the UDL, plus 2.5, consider this as a 2.5, which is the moment at the end C. So from this we get RC equals to 9.98 kilonewton, and if I back substitute this value in the summation of vertical forces equation, then I am going to get a RB2 value which comes up to 20.02. Now if I add the values of RB1 from span 1 and RB2 from span 2, then I will get a total value of reactive force at the joint B, which is common between both the span, which comes to 42.20. Once I know the reactive forces, then I am able to prepare the shear force diagram, which appears like this. At end 27, end A 27.82, at end B it will have the variation from positive to negative due to the application of the load and the contribution of both the span. Now similarly, I can have the bending moment distribution over the span. The fixed and bending moment has been shown here, which we have derived from the three moment theorem. Now to get a net bending moment across the beam, I have to overlap it with a free bending moment, free edge bending moments of this particular beam. So we'll get here the envelope which is going to have overlap with a positive and negative axis, and this area under this envelope is called as a net bending moment diagram. Likewise, we will be able to solve the numericals with the help of TMT method. Hope you understand. I will come with further more numericals with a clearance of the idea with reference to different cases in next lecture. Till then, have a good day. Have a good time.